In this question, we are given a number of elements and their atomic weights, also known as relative atomic masses, that are experimentally measured. By the way, these are their approximate atomic weights. And in each case, we have to find out the atomic mass, molar mass, and the mass of 1 gram atom. I will work them out for a couple of elements listed here and leave the rest as an exercise for you. Let us take the case of boron. The approximate atomic weight of boron is 10.8. Then what will be its atomic mass? It is simply 10.8 U. You simply have to express its atomic weight in unified atomic mass units to get its atomic mass. So this is the mass of a single boron atom. But if you want its mass in kilograms, for whatever reason, you know how to do the conversion. You know that 1 U is approximately equal to 1.66 times 10 to the power of minus 27 kilograms. So this is the atomic mass, or the mass of a single boron atom in kilograms. Then what is the molar mass of boron? Molar mass is represented by the symbol capital M, and the particle for which the molar mass is represented is indicated by writing the symbol or the formula of that particle next to this symbol. Here we are representing the molar mass of boron, which is composed of boron atoms. So we write the letter B in parenthesis next to this. So this indicates that we are representing the molar mass of boron atoms. And to get the molar mass of atoms, you have to express its atomic weight in grams per mole. Atomic weight of boron is 10.8, so it will be 10.8 grams per mole. That is the molar mass of boron. That is mass per 1 mole of boron. And 1 mole of boron contains an Avogadro's number of boron atoms. Then what is the mass of 1 gram atom of boron? It is simply, again, its atomic weight expressed in grams. So 10.8 grams of boron is 1 gram atom of boron. Again, it contains an Avogadro's number of boron atoms. Now let us take another example, say nickel. Its atomic weight or relative atomic mass is approximately 58.7. Then what will be the atomic mass of nickel? It is 58.7 U. And in kilograms it would be 58.7 times 1.66 times 10 to the power of minus 27 kilograms. So this is the atomic mass of nickel, or the mass of a single nickel atom in kilograms. And this is the same in unified atomic mass units. Then what will be the molar mass of nickel? You know that nickel is a metal and it is composed of nickel atoms. So here we are talking about the molar mass of nickel atoms, and that is represented by this symbol of nickel next to M. Again, for atoms, molar mass is again its atomic weight expressed in grams per mole. So the molar mass of nickel atoms is 58.7 grams per mole. And the mass of 1 gram atom or 1 gram atom of nickel is again its atomic weight expressed in grams. So if you take 58.7 grams of nickel, that means you have 1 gram atom of nickel. And remember, 1 gram atom of any element contains an Avogadro's number of atoms. I leave the rest of the elements as an exercise for you. And in the next question, we are given the formulae of many substances and we are asked to find out these in each instance. Again, I will work them out for a couple of substances listed here and leave the rest as an exercise for you. Here we have chloroform, and chloroform is a covalent substance. Therefore, it is a molecular substance, that is, it is composed of chloroform molecules, and this is the molecular formula of chloroform. Now, given the molecular formula, how do you figure out its molecular mass? To figure out its molecular mass, first you have to calculate its molecular weight, also known as relative molecular mass. How do you calculate that? Simple. You multiply the atomic weight of each element present in the formula with its subscript and add all those products to get its molecular weight. The atomic weight of carbon is approximately 12.0, and the subscript of carbon in this formula is 1. So 12.0 times 1 plus, and that of hydrogen is 1.0 and its subscript is 1. And the approximate atomic weight of chlorine is 35.45, and the subscript of chlorine in this formula is 3. So if you add up these three products, you will get the molecular weight of chloroform. Now let us simplify this expression. This expression has three terms, and each term is a product of two values. If you look at this value, this is a counted number. We simply counted the number of carbon atoms present in one molecule of this compound just by looking at its molecular formula. Therefore, we are 100% sure about its value. There is no doubt or uncertainty in our mind about its value. It is exactly 1. That is why we say counted values are exact values. To indicate that we know their values exactly, sometimes we say that we know their values up to an infinite number of decimal places. And if you know some value exactly or up to an infinite number of decimal places, that means its precision is infinity, or in other words, it has an infinite number of significant figures. So remember, all counted values are exact values, so they have an infinite number of significant figures. Whereas this is an experimentally measured value. Remember, all the atomic weights listed here are experimentally measured, and you can never measure the value of any physical quantity up to an infinite number of decimal places. Only if you measure the value of a physical quantity up to an infinite number of decimal places can you say that you know its value exactly, and you can never do that experimentally. Therefore, all experimentally measured values are inexact values. And in this case, we are able to measure the atomic weight of carbon only up to 3 meaningful digits. And on top of that, we are not 100% sure about the value of this last digit. That is why we say they are inexact values. Now, to understand the precision of such values, you have to figure out the number of significant figures. I have explained that in another video, so kindly refer to that. In this measurement, there are 3 significant figures. Now, when you multiply these two, the result must have only 3 significant figures. Now, when you multiply these two values, you would get 12.0, and that also has 3 significant figures, so we are good here. Here there are 2 significant figures, here infinity, and the result is 1.0, and it should have 2 significant figures, and it has 2 significant figures, so we are good there also. This has 4 significant figures, this an infinite number of significant figures, the result must have 4 significant figures, but the result is 106.35 that has 5 significant figures. So in that case, what should you do? You should round the value. But remember, we are not yet done with our calculation. In a multi-step calculation, rounding should be delayed until the last step. So remember that there should be only 4 significant digits in this value, but use all the 5 digits for the purpose of addition. Then you will get 119.35. Now we have to check and round this result if needed to make sure that it is not more precise than what it should be. That is to make sure that it does not contain more significant figures than it should. Remember, this result is obtained by the addition of these 3 values. Then what does the addition rule tell? It tells the number of decimal places in the result must be same as the number of decimal places in the value that has the fewest number of decimal places. In this case, there are 2 decimal places. In this case, there is only 1. In this case also, there is only 1. So the result must have only 1 decimal place, but in the result we have 2 decimal places. So we have to round this number by dropping this last decimal place. And this is the last digit that we want to keep, and this is the first digit or the only digit that we are dropping. And it happens to be a 5. If it is a 5, how do we round it? We have to look at the last digit that we are keeping, and that is a 3, and it is an odd number. If that is an odd number, we have to add 1 and drop all the unwanted digits. Then upon rounding it becomes 119.4. So this is the molecular weight or relative molecular mass of chloroform given these atomic weights. Now if the molecular weight of chloroform is 119.4, then its molecular mass would be 119.4 U. That is the mass of a single molecule of chloroform. You simply have to express it in unified atomic mass units. And if you want its mass in kilograms for whatever reason, you know how to do that conversion. Then its molar mass is its mass per 1 mole of chloroform, and 1 mole of chloroform contains an Avogadro's number of chloroform molecules. So its molar mass will be equal to its molecular weight expressed in grams per mole. Then the mass of 1 gram mole or 1 mole of chloroform, of course in the old sense, would be its molecular weight expressed in grams. And you know, 1 mole of any substance contains an Avogadro's number of molecules. Now let us work out another example. Let us pick nickel phosphate. It is an ionic compound and this is its formula unit. Then how do we calculate its formula weight or its relative formula mass? Same as before. And the atomic weight of nickel as listed here is 58.7, and that of phosphorus is 31.0, and that of oxygen is 16.0. So it would be 58.7 times 3 plus 31.0 times 1. The subscript for phosphorus here is 1, plus 16.0 times 4. The subscript for oxygen is 4. And we have 2 such units, so you have to multiply this whole thing with 2. And upon simplification and applying the rounding rules correctly, you must get a value of 366 for the formula weight of nickel phosphate. Then what would be its formula mass? That is the mass of 1 formula unit of nickel phosphate. Simple, it is 366 U. And you know how to convert it into grams if needed. Then what is the molar mass of nickel phosphate, that is mass per 1 mole of nickel phosphate, and 1 mole of nickel phosphate contains an Avogadro's number of formula units. Therefore, the molar mass of nickel phosphate would be its formula weight expressed in grams per mole. Then what would be 1 gram formula weight of nickel phosphate? Simple, again its formula weight expressed in grams. As simple as that. Now what about ozone? Ozone is another form of oxygen, and it is composed of ozone molecules, and in each ozone molecule there are 3 oxygen atoms. So the atomicity here is 3, and the atomic weight of oxygen is 16.0. So when you multiply it with its atomicity, you would get its molecular weight, that is 48.0. Then what is its molecular mass? That is mass of a single ozone molecule, that is 48.0 expressed in unified atomic mass units. Then what is the molar mass of ozone? Again, ozone is composed of ozone molecules, so therefore molar mass of ozone would be its molecular weight in grams per mole. Then what would be the mass of 1 mole of ozone? It is simply again its molecular weight expressed in grams. It would be 48.0 grams, as simple as that. So 48.0 is the molecular weight or the relative molecular mass of ozone. 48.0 U is its molecular mass, that is the mass of a single ozone molecule. 48.0 grams per mole is its molar mass, that is mass per 1 mole of ozone that is composed of ozone molecules. Again, 48.0 grams is 1 gram molecular weight or gram molecule or gram mole or simply mole of ozone, and 1 mole of any substance contains an Avogadro's number of molecules. And I will leave the rest as an exercise for you.